Okay, folks. So rather than go over this in class, since we had to do an online test and we lost some days for that and the snow, I'm going to go over it here on this video. So if you want to see why you got something wrong, the video here. So starting with number one. Number one, place the bond compounds in order of increasing boiling point. So you want to check on the forces. We have dispersion, we have dipole slash hydrogen bonding, and we have ion dipole. So this one's just London dispersion forces and butane. This guy, because we have the oxygen sodium, we're calling that ion dipole. Isobutane, also London dispersion forces. And this guy, ethylene glycol, because of the OHs, that's hydrogen bonding. So no matter what, you should have the hydrogen bonding and the ion dipole at the highest. Now, the two London dispersion forces, you got to go, okay, so what differentiates the two? One is linear, one is branched. This branch, the shape, they weigh the same, they have the same chemical formula, but one of them, the shape is a little bit bulkier and it's harder to get that closer together. So isobutane ends up being the lowest, followed by N-butane, followed by ethylene glycol, and then lastly, sodium acetate, which sodium acetate is a solid at room temperature. Ethylene glycol is a liquid. Now, what type of solid is stabilized by a delocalized sea of electrons? That is metallic. Nothing to argue about there. This one, a little tricky, but not too unreasonable. If deionized water is 100% water by mass, and the density is 1 grams per mil, what is the molarity? So we have right here 100 grams per 100 grams. We need to turn this part to moles and this part to liters to give you the molarity. 100 grams divided by 18 grams per 1 mole is going to give you something like 5.55 moles. 100 grams at 1 gram per 1 milliliter, and knowing that there's 1,000 milliliters in 1 liter will give you 0.11 liter. So if I take 5.55 divide by 0.1, the decimal gets moved 1 over, and so you get 55.55 repeating, or essentially 55.6. Not too bad. Or at least it shouldn't be too bad. I wanted the molecular formula, the empirical formula, really. The antifluoride is just the name of this shape. The big thing here is we have lithium and we have oxygen. Those are the only two types of atoms. The lithium, kind of silver, and the oxygen, black. The oxygens are in a face-centered cubic. Face-centered cubic means we have the edges, so we have the corners, which means a 1 atom, and all the faces, which is another 3 atoms. So there's 4 oxygens. The lithium are all in the body. They're in what would call, I think, I'd like to say tetrahedral holes, all the tetrahedral holes, but we have 8 lithiums, the body. Now, to make this, to simplify this, it's going to be Li2O. 8 and 4 simplify to 2 to 1. I gave you partial credit for Li8O4, but full credit you had to have Li2O. Last 2 on the first page. Benzene has a pure vapor pressure of 100 torr. what would the vapor pressure be if 10 grams of anthracene were mixed into 50 grams of benzene? To get the vapor pressure, the equation is P equals X of benzene times P naught. So we have P naught is 100 torr. So we have to find the mole fraction of benzene. So 50 grams of benzene, 12 times 6, 12 times 6 plus 6 is 78. So how many moles of benzene do we have? So 50 divided by 78, it's about 0.641. Now we need to find the moles of anthracene. 10 grams, the molar mass of anthracene, 14 times 12 plus another 10. So that's on like 178 grams in 1 mole. How many moles is that? 178. It's 0.056. So mole fraction, I'm going to move this over here. Mole fraction would be 0.641 divided by 0.641 plus 0.056. 641. So 0.697. So 0.641 divided by 0.697. The mole fraction is 0.9. We'll say 1. We'll say 920. So 0.920 times 100. What is the vapor pressure? It's D. Drops by just a little bit because there is so little anthracene. It weighs so heavy and it's so little. So it gives you such a small contribution. But it's enough to drop it 8 torr. If you got A, you use the mole fraction of anthracene. And so you calculate the drop, not the actual new vapor pressure. This one, a little bit tricky, but I tried to give you as much hint as you needed. Your equation is solubility equals K sub H times pressure. Solubility, that's another fancy way of saying molarity. So 1.56 times 10 to the negative 4th M equals 1.3 times 10 to the negative 3rd M per atmosphere times our P. Following the units, what do I have to do? I have to take your solubility divided by K sub H, and that will give us our P. So really, all you have to do is 1.56 times 10 root negative 4. Divide that by 1.3 and 10 root negative 3, and you'd get the answers. The answer is 0.120, which is good because how much oxygen is actually in the atmosphere? It's closer to 0.21. So there's excess oxygen in the atmosphere. It's enough, well enough for most fish to live. Camphor oil is notoriously sensitive to impurities with a K sub F of 37.8. If 1 gram of turpentine, similarly weight, is mixed into 100 grams of camphor, what temperature will its 176 melting point drop to? So delta TF equals K negative KF times M. So we have to find M. M is moles of turpentine in kilograms of camphor oil. So 1 gram. So turpentine, C10H14. So I think it's 12 times 10 plus 16, 136, I think. I'd like to say. Yes, 136 grams in 1 mole. And then I'll divide that in 0.1 kilograms of camphor oil. So 1 divided by 136 divided by 0.1. So the molality is very, very low. 0.07, we'll say 4. Well, our delta T, the temperature that it's going to drop, delta T is equal to negative 37.8 times our 0.074 times 37.8. How much will the temperature drop? It will drop by delta T, say it'll drop by something like negative 2 points, we'll say 2.8. Negative 2.8, that's our delta T. Now, since the original melting is 176, it drops by about 3 to 173. Now, that's not to say, well, that's not a big drop. You mixed 1% of an impurity that weighs just the same, 1% by mass of impurity that weighs the same. Like you didn't add the oxygen onto there. 1% of that mixed in, and it drops by 3 degrees. So imagine if you mixed in some solvent like acetone that weighs like way less, like 1 divided by 44 or something like that. Well, you would have something like 0.2, and then 0.2 times 37.8. If you mix the same mass of acetone in, you would lose close to 8 degrees of temperature. So it's going to keep dropping down 1 gram if it's smaller and smaller. But moving on to 8. Which of the following solids would you expect to have a high melting point, low electrical conductivity in the solid state, and a high solubility? So high melting point, that knocks out molecular. Low electrical conductivity, that knocks out metallic. But the solubility, that is going to be A all the way. So ionic. Note, I said conductivity in the solid state. In the liquid state, well, in the aqueous state, oh yeah, it's perfectly conductible. But solid state, no. Okay, we're going to use the phase diagram for the next couple problems. What would have to be done to get supercritical N2 from a standard temp and pressure? Standard temp, that's about 298. So about, notice it's Kelvin. Pressure would be about here. What I have to do, move up. So that means increase the pressure. Now, what temperature and pressure would the triple point be achieved? This is the triple point. Each of these markings, if you count them, 1, 2, 3, 4, 5. There's 5 markings. 1, 2, 3, 4, 5 for every 200, for every 100. So each of these markings is worth 20. So you move this up. The temperature is about 60 Kelvin. The pressure is about 10 to the negative first, or 0.1 atmospheres. I gave points for whether you had the units, and if but you had to have some version of that to get full credit. Now, which compound would you expect to have the highest vapor pressure? So the highest vapor pressure means the lowest forces. The lowest forces. So this guy, that's clearly hydrogen bonding. So you might expect that guy to have the highest, this guy also has hydrogen bonding. So once again, no. You got this guy, which is dipole. This guy is just going to be London dispersion forces. The thing of it is here is that chlorine, while not being the most polar element, is more polar than sulfur. More polar than sulfur. Now, I originally wanted to put dimethyl ether in there, but because of the nature of that one is actually very weakly polar. And so you were kind of fighting between this guy and this guy. This guy would have been the correct answer. And not because it kind of breaks the trend. But this guy, sulfur, is about the same polarity as carbon. So for all intents and purposes, it is non-polar at all. So the correct answer is B. B should have the highest vapor pressure. Last one on this page. What would the osmotic pressure be of 30 grams of sodium sulfate dissolved into 1 liter of water at 25 degrees? So 30 grams, turning that into moles in 1 liter. So 30 divided by, so we have sodium as 23. There's 2 of them. And sulfur is 32. And oxygen is 16. And there's 4 of them. So you get 0.2112. I gotta actually write this down. Can't just jump steps. Okay, so that's 142 grams per 1 mole. And then, because it's 1 liter, that's the molarity. Osmotic pressure is pi equals I mRT. Well, the trick here is this breaks apart. It breaks into 3 ions. 0.2112 times R, 8206, times T, 298. Got to be in Kelvin. So 0.2112 times 298 times R times 3. Correct answer is 15.5. 15.5. Last page. Which of the following aqueous solutions would have the freezing point be the lowest? We have 1 molar, 1 molar, 1 molar. So we can't use molality. Organic. All covalent. So when it's all covalent, I is 1. So the correct answer is D. Once again, I want the empirical formula, the mixture of these guys together. So how many arsenics? There's 2 arsenics in the body. Those are 2 arsenics in what we call octahedral holes. And we have how many nickels? We have nickels in the corner. So that's 1. And nickels in 1 set of edges. Edge. Each set of edges is 1. Now, if there was a set of edges there, that'd be another 1. Or a set of edges there. I mean, we're missing 2 sets of edges they could be in, but they're not in there. So we have a ratio of 2 to 2. So an Ni2 and As2 simplifies to 1 to 1. Once again, if you put the 2 to 2, I gave you partial credit. I gave you an E. Which of the following actions would decrease the solubility of a gas? It's not increasing the pressure. Increasing the pressure is the only thing that increases the solubility. Gas is the only thing that's made more soluble. Here's where you have to think. Increasing the volume of the liquid. No, that always increases solubility. You add more water, it becomes more soluble because the concentration goes down. The only thing, increasing the temperature of a gas makes all gases less soluble because they have more energy, easier to escape. Last two is that vapor pressure of water at 20 degrees is 17.535. What temperature would the vapor pressure be? 760 torr. Now, this one's actually quite easy and quite tricky. Easy in that you can actually guess and get it right if you know anything about Kelvin. That is 293 Kelvin. So pressure goes up, torque goes up. So the temperature must go up. So which of these is greater than 293? 370. If I turn that back into Celsius, perhaps, what would that be? That would actually be 97 degrees Celsius. What is the boiling point of water? 100 degrees. So what should it be? That one. But how would you do it normally? ln P1 over P2 equals delta H over R, 1 over T2 minus 1 over T1. So we have ln of 17.535 over 760 equals 44,020 over 8.314. 1 over T2 minus 1 over 293.15. Okay. Evaluating this, you say, okay, so we have ln of 17.535 over 760. You get that to be negative 3.769. You multiply by 8.314 divided by my 44020. You get something like negative 0.000711, we'll say 9 equals 1 over T2, 1 over 293. You add your 1 over 293.15. You get something like 1 over T2. You get 1 over T2 is equal to 0.002699. And then you invert that puppy and you get 370.5. So the answer is still mathematically 370. But as I said, critical thinking tells you there's only one possible answer. Only one possible answer. Pressure goes up, so must temperature. Pressure goes down, so must temperature. Lastly, what type of solid would you classify this? This is an allotrope of carbon. Technically, what I was looking for was a covalent network solid. However, one could argue that C60 forms an individual molecule that can't really be simplified, so I also accepted molecular. Molecular solid also worked as well. But I was looking for covalent network solid. But that is and was test 1.